Hello and welcome to the Maker Studio workshops. This workshop will be on programming an Arduino in tinkercad. This is the circuits module in tinkercad. Please navigate to the website tinkercad.com and click on the Join Now or Sign In options. If you haven't already done so, please create a tinkercad account. Here, I'm going to use the Sign In with Google options, and it will link to the Maker Studio account. Once I sign in with Google, I have access to the 3D models in the Maker Studio account. Your view is going to be different because it's associated with the account you make. There are several tabs, and the 3D Models tab will display as a default. You can also access the Circuit tab, the Code Block tab, and the Lessons tab. For this workshop, we're going to the Circuits tab, and we're going to create a new circuit. This is the part of the workshop where we will talk about Arduino rather than just talking about the electronic design component of this module. tinkercad has created a simulator that simulates electricity and electrical components. You can create your own circuits and test them so that you know that they would work in real life if you were to build the same circuit. Imagine you're just getting into electronics design, but you don't want to spend a lot of money to get the parts first. What you can do here is use parts and simulate electricity. When you have something that you've designed that works, you can purchase the parts off of DigiKey, off of SolarBotics in Calgary, or Amazon if you choose to use that service. To get started, look on the right-hand side. We're going to see there are components available to use. And notice how this is the basic component configuration. You can have access to all components, in addition to starter kits. For this workshop, click on the All Components tab. These components have been arranged depending on what they can do. Scroll down to the bottom, you'll notice that there's the Arduino, and this is the Arduino Uno revision 3. Drag this onto the working plane. Notice how it names your Arduino as one, and you can name it just Arduino. Zoom in and out. If you're using a mouse, use your scroll wheel, or if you're on a PC or a Mac that's a laptop, you can scroll using the two-finger gesture on your trackpad to zoom in and out. You can move your components around if you click and drag the component itself, but you'll notice very quickly how we can't tell it's moving in relation to anything. There's nothing else on the working plane. We'll drag out a breadboard so that we can see the components move in relation to each other. So drag these components around to practice and zoom in and out. Let's say you want to rotate your components so that they're easier to place on the breadboard. For instance, a resistor. Let's grab a resistor and drag it onto the working plane, and we can see it here. We can see that it has a name, and we can see information about the component itself. For instance, the resistance in kiloohms. We can also change the resistance to be 1 ohm, but for this workshop, we'll leave the resistance to the default of 1 kiloohm. Positioning this on the breadboard is important because for electricity to flow through a path, it needs to actually have a path to flow through. This component cannot be positioned on the breadboard this way. We need to rotate it. To rotate objects, you can use the rotate button. Now, when we place this onto the breadboard, it's going to create an electrical path between the terminal 30 on the breadboard and terminal 26. And we can plug it into something like digital pin 1, or however we're going to use this resistor in our electrical circuit. To draw wires is simple. Click on a terminal, and every time you click, it'll draw an anchor point so that you can shape your wire into any shape that you want. Mostly wires will connect terminals, and this one we will plug into the digital pin 2 terminal on the microcontroller. Notice how these points become anchor points that can be positioned in addition to deleted. You'll notice that when it is selected, the point will turn white. And you can also select multiple points by holding Shift. They'll turn white and you can drag those to position them. If you would like to deselect, just click on the working plane. Click on your components and hold Shift to select multiple components. To delete the components, go to the Delete Trash Bin icon at the top left-hand side. Now let's look into the Arduino itself. To access the ability to program or work with the code on the Arduino, you need to click on the Code tab. This will take you to code blocks. For this workshop, we're going to use the text-based programming options. Click on Text and say yes to, are you sure you want to remove the block code editor? This introduces you to programming in Arduino. Arduino, the language, is a subset of the programming language C. All Arduinos that exit their factory are tested with a program that's installed on them. This program will blink an onboard LED. This onboard LED connects to the 13th pin. The 13th pin and the onboard LED indeed share an electrical path. Let's start the simulation. What you can see is that it is plugged in, the power is being supplied by the USB connection, and we can observe the onboard LED is flashing. Let's take a look at the code. We can see there are two parts of the code, the void setup function and the void loop function. And in the void loop function, there is a digital write command that is writing to the 13th pin a high signal. Then delay is called to hold that high signal, and it is again followed through with digital write to the 13th pin a low signal, and again another delay. The delay is 1000 as a parameter, and that translates to 1000 milliseconds or 1 second. So let's change some of the parameters in the code, and what we can do easily is change how fast the light blinks. This will allow you to see how these commands take parameters, and it's the parameters that are passed to the commands in the brackets that create the behavior of what the command will do. Let's change the parameters in delay to only be 100 milliseconds. This is a comment, and it is indicated by 2 forward slashes. We should try to keep accurate comments, which means I should really change that to say it's 100 milliseconds, but the comments are irrelevant for the IDE. They are not run when you execute your code, or you start the simulation in this case. But let's keep accurate records, so we'll change our comments to match the parameters in delay. Start your simulation. And now the light is actually flashing so fast that we can barely see it turn on or off. It is doing it, but it's way too fast for our eyes to register it. This is introducing how fast the microcontroller can actually run. So we have to fix this. Let's stop the simulation and instead increase the delay to 10 seconds. Once you've changed the delay, you can start the simulation again. And the delay is indeed 10 seconds. There, the light turns off. This will repeat until the microcontroller, the Arduino, loses power. And how is it going to lose power? Well, you can just unplug it. We'll stop the simulation, and now you're free to play with some of this code. Let's start by dragging a breadboard onto your working plane. You can use the small breadboard and zoom so you have a better view. Now we're going to drag out a 9-volt battery and connect the negative terminal of the 9-volt battery to the negative terminal on the breadboard. We'll connect the positive terminal of the breadboard to the positive terminal of the battery. Let's change the wires to correspond with electrical standards. Red wires should be power connections and black wires refer to ground connections. Please change these wire colors now. You can do so with the drop-down menu when you select the wire. Now let's drag a button or a push button from our basic component bin on the right-hand side. You can plug it in anywhere on your breadboard. Notice how the green indicates that the terminal you are hovering your mouse over is conductive in that direction. Power rails are horizontally conductive, and the terminals, lines 1 through 30, are conductive on a vertical plane. For example, terminal 2 here will connect along the green indications. All of those are sharing an electrical path. Power shares an electrical path all along the power rail, and so does ground. Let's take a look in the basic component bin for the LED. Please drag this out onto your working plane and plug it in on your breadboard somewhere. What we're going to do is connect the LED to a push button, and we need to use a resistor. Drag this onto your working plane and use the rotate button to be able to rotate the resistor into a position that can connect on the breadboard correctly. What I'm referring to when I say connect correctly is that conductivity is the connection in which electricity can travel through an electrical path. In this case, the electrical path is conductive through the cathode of the LED, through the resistor, and it needs to connect to the button. It's not going to connect to the button, so you'll have to shift it over so that it does indeed fall on the right paths. In this case, terminal 15 to 19, with the resistor joining the two components in between. We're now going to tap power from the power rail and take a wire and connect it to the anode of the LED. If you hover the wire over the 20 line terminal on the breadboard, you'll see that the socket will actually grab the wire. Let's try this again on the other side of the button. Drag a wire from 19 terminal, in this case, and drag it to the ground connection. Once you have plugged in those two wires, your circuit will have continuity. What this means is that it is electrically closed and electricity can flow through the circuit. Go ahead and change your wire colors to match electrical standards. Now when you press the Start Simulation button and you press the button, the circuit should be closed and thus the electricity can flow through the LED. Let's stop the simulation and remove the resistor to test what would actually happen if there was no resistor in the circuit. Join the cathode from the LED to one of the terminals, terminal 2A, on the button. If you press the simulation button at the top right-hand side and you click on the button on the breadboard, the LED will now show you that it's exploded. In fact, there's a current rating for LEDs, and this one was rated for 20 milliamps only. If you observe, the current that was able to pass through the LED was 915 milliamps. That's quite a bit more current than that LED is rated for. So what a resistor does is it limits the amount of current that can pass by resisting the flow of electricity. Resistor is the name for that component, and it's easy to say in your mind resisting electricity to remember what it's used for. Imagine if you had a 20-foot long wire, a copper wire for instance, and you passed a 9-volt signal through that copper wire. Because of the length of the wire, there's a lot of molecules of copper that need to transport that 9-volt signal. And what happens when that low of a voltage travels through that length of a wire is that eventually it loses its electrical charge. That is lost in heat energy as it travels through the wire. A resistor relies on the same principle, but a resistor is designed to limit a very specific amount of current through itself. We've learned how to use simulated electricity and create our own electrical circuits in tinkercad, but now we need to find an Arduino. On the right-hand side in your components bin, with all selected, please scroll down until you find the microcontrollers tab. Drag the Arduino onto your working plane and you're ready to start the lesson. All Arduinos are manufactured in factories and they need to be tested before they're sold to consumers. By loading an Arduino program onto the boards before they leave the factory, the manufacturers can assure the quality control of these products before they leave the factory. Let's take a look at this program. Press the Start Simulation button, and as soon as you do so, you'll notice that there's an onboard LED on the microcontroller that starts to flash. This is an example of the behavior that is written into the program to test the board. The board's working, the LED is flashing, and because this is a simulation, we can even open the code tab and take a look at the code that's living on this board. Normally, you can't actually see what has been written in an Arduino. Let's say you unplug your Arduino, put it on your shelf, and a couple years later you want to find your code. Unfortunately, you can't connect it to a computer and have access to the code. It needs to be saved on the computer itself. But let's open the code tab and take a look at this program. You can see when you open the code tab that there is block code. For anyone who's familiar with Scratch, this is a similar method of programming. As you'll notice, the commands and the functions that have like uses have been grouped via colors. If you click on the various options, you can see that there are additional functions in those bins. Always make sure that you stop your simulation to edit your code. Click on the Blocks tab and we're going to select Text. It'll ask you if you're okay with losing all of the block code that you've made. You can say Continue for this example. If you have been using the block code editor, make sure that you're okay with moving to text. It won't allow you to revert back to block if you have been writing in text. We'll now see a view of this text editor that looks more like an IDE. What is an IDE? An IDE stands for Integrated Development Environment, and it is the software that you use to write programs in. This is where you can write your source code. This is the portion of an integrated development environment that is called the text editor. You can see that this program occupies lines 1 through 16. Why are the lines numbered? This is if an error is presented or there is a bug with your code. The IDE will also check to see where the error is, and it will indicate what kind of an error as well as on what line it has occurred. You are now about to learn how to program in Arduino, or a subset of the language C. This source code is referred to as a sketch. Notice that there are two distinct sections of these programs. There's the void setup and the void loop. When we run this program, we can see what's happening because we're looking for the behavior of the LED. The first thing to note is that there is a function that is being used to assign a pin to an output, and this is occurring only once. Why does it occur only once? It is nested within the void setup function. Take a look at pin mode. This is a command that assigns a pin at a location, 13, to an input or an output. On this command on line 7, we can see that pin mode is the command that is called. It is being told that on pin 13, it's going to pass an output signal. That means that electricity is sent out from that pin. But wait a second, there's nothing plugged into pin 13. Well, we can actually tell from this example that pin 13 and the onboard LED share an electrical path. Whatever is done to one will affect the other because they are connected. This is only really used to test code without having to use an LED for an output, and it only really works to test the 13th pin as an output. Any of those digital pins from 0 to 13 can be inputs and outputs, which means that as an output, it sends electricity, but as an input, it's listening for electricity. Did it receive electricity? If it does, you can use that to make a decision. Let's take a look at the void loop section of this source code or program. When we see void loop and there's a bracket and a close bracket, what immediately follows is a curly bracket. This curly bracket is part of C syntax. And what that means is that the curly bracket is used to indicate that everything within that curly bracket and the closed curly bracket on line 16 will be run inside of the void loop function. So if the void loop function is repeating, that is what is creating the animation. Let's learn more about how to digitally write to a pin and what's happening on pin 13 by creating an LED circuit and connecting it to pin 13. Let's close the code tab on the top right hand side and find in our circuits bin an LED. Drag the LED onto your working plane, and why not for fun just change the color to be green or blue or purple? I'll let you decide. Drag an LED from the components bin onto the working plane and practice using the rotate button on the top left-hand side. You can connect components without a breadboard, and for a simple circuit like this, it's highly advised. Just drag the resistor to the cathode leg on the LED and they should connect. Now, from the exposed terminal leg on the resistor, connect this with a wire to ground. We're going to close our circuit at this point by connecting the LED to pin 12. But what happens if you actually turn the simulation on? Well, nothing happens. And do you know why? We haven't actually reassigned the pin to reflect the wiring. It's plugged in to pin 12. Stop your simulation, and we're going to open the Code tab. What I want you to do now is find every place that it says the pin 13 and change this to be pin 12. Let's press the Start Simulation button, and because you've wired the LED into pin 12, this will work just fine. Please stop your simulation, and we're going to, at this point, do some optimizing. Can you find where your pins are called? They're called on line 7, line 12, and line 14 of the text editor of this IDE. Why don't we create a variable and just pass that variable to each place where it is required in the parameters of pin, mode, and digital write. To declare a variable, let's go to the global variables section of this sketch. The global variables are declared at the top of your sketch. To declare a variable, you'll have to specify the data type that will be contained within that variable. Type int for integer, and now declare the name for the variable. This will be the container that will hold the data type. Green LED is what we'll use in this case. Now we'll call an assignment operator of an equal sign and pass it the value that we want to store inside of that variable name. Add a semicolon after the number 12 and you've terminated the line. This means that the program can continue to execute the rest of the code. But what if you don't include a semicolon after your declaration of a variable? Press Start Simulation and it'll generate an error code. This is telling you that on line 2, there's an error. A semicolon is missing. Please add that semicolon and your line is terminated. Then the program knows it can continue to execute the rest of the lines. Start simulation, but there appears to be something wrong. The LED isn't turning on. The code is correct. There's no error messages being returned from the IDE to the console, but notice how the simulator is actually not incrementing. There is no simulation time that's incrementing. I've noticed that this is a bug with the tinkercad IDE, and you can just simply refresh the browser. All of the work that you've created will auto-save, and it'll also save onto your personal account you've made in addition to saving under this unique name that can be searched. You can click on that unique name and you can rename the project so it's easier for you to understand and find later. So we'll call this very didactically Arduino demo for the web. As you see, this is on the library website, so it's good to name your projects as literally as you can in order for you to be able to find them easier once you've created a whole bunch later. So now when we start simulation, the time is incrementing, so the IDE hasn't jammed up and it's running fine. So now we should use that global variable. Press the Stop Simulation button to get access to the code and change the parameters for the code that is required to assign a parameter of the pin and use the name of the global variable instead. In this case, that name is green LED. You'll replace this on line 7, line 12, and line 14 in this example. Start simulation, and it's working. But what have we really done here? Well, we've made it more efficient for us to be able to prototype. If you need to unplug the wire and plug it into a different pin, you would have to write 3 times where that pin is. Instead, now that we've used a global variable, we can change that on one line. And now when we start the simulation, you can see how from a code perspective and from an electrical perspective, it becomes much easier to just change where things are wired in one line of code. Let's now include another LED that's connected to a different pin. Because you have already learned how to plug an LED in, I'm going to fast forward through this video, but feel free to pause so you can see the wiring. So we'll have to pull an LED out, get a resistor, and rotate that resistor. Connecting the resistor to the cathode of the LED, we'll take a wire from that leg and plug it into ground. You can have more than one ground connection plugged into the same ground port, which you couldn't do in real life. Now we're going to take the anode and connect that to a pin. I would recommend changing the colors of your wires so it's easier for you to tell what LED is plugged into what pin. You can do that just by selecting the wire and changing its color, and I do recommend making all of your ground connections a black wire. This is an electrical standard. We're going to now integrate a photoresistor in this electrical system we're creating. We're going to have to find the components, so scroll down and drag a photoresistor out onto the working plane. We're also going to need to use a resistor as a pull-down resistor connected from one of the legs of the photocell. Please drag a 1K resistor onto the working plane. You can connect these components together, just connect the resistor to one of the legs on the photocell. We are now going to connect from the resistor to ground, and notice how there are additional pins for ground on the microcontroller. In fact, there are 3 pins. We learned about the ground pin on the top of this board. There are also 2 ground pins on the bottom of the board, located here. We're now going to have to connect the photoresistor leg on the side that hasn't been connected to a power supply, and in this case we can use 3.3 volts, but let's use 5 for this example. We've now closed our circuit and this photocell is receiving an electrical signal, but let's remember to change the colors of our wires so that we can easily tell that there is a signal of power or 5 volts coming in on a red wire, and change all of your ground wires to be black. But what we've just done is the equivalent of plugging a light into a wall socket. We're supplying power to something that is not returning to indicate its state. Is the light on? For instance, if we use our eyes, we can tell a light has been plugged in because the room is bright, but this photocell actually needs to have a third wire connected from where the pull-down resistor connects the photocell to the ground pin on the microcontroller. And this is so that we can actually tap the electricity and read it on a pin. Remember how we were talking about pins being inputs and outputs? Well, I'd like to introduce the analog pins. These are located on the bottom right-hand side of this board, and they're named between A0 to A5. What's so special about analog pins is that they don't actually read an on-off signal. They can actually read a range of numbers that are actually the voltage. So in this case, if we're sending electricity and this resistor is resisting the current, we can actually read, using an analog pin as an input, how much it's resisting. And what that translates to is if it's resisting a lot, the room is very dark. If it's resisting less, the room is bright. At this point, we need to connect the electrical circuits that we've just built, the photoresistor and the red LED. Declare a new variable in the global variables. This will be the red LED. Use an assignment operator of equals and pass it the pin. Number 2, it's plugged into pin 2. Use the semicolon to terminate your line. Now we're going to have to get inside of the void setup function, and we're going to have to connect the pin using the pin mode command. Simply call the command by typing pin mode. Watch your capitalization on the second word. Then use a bracket and pass it the variable that you have assigned to indicate the red pin. Pass the pin mode function the second parameter, setting it up as an output. Use a close bracket and a semicolon to terminate the line. Let's go back to the global variables and assign another variable for the pin that the photoresistor is plugged into, A0. Declare your data type as an integer and give it a variable name that's meaningful. In this case, we can just use photoresistor. And because photoresistor is 2 words, we'll use camel case, where resistor, the first letter of that word, will be capitalized. Use your assignment operator and pass it A0. That's the pin that the photoresistor is plugged into. Use your semicolon to terminate the line, and you can move on. What we now need to do is connect the pin of the photoresistor with a pin mode in void setup. Please use the same command that you've now written a few times and pass it the correct variable that contains your pin as the first parameter for the pin mode command, and pass it the second parameter. Is it an input and an output? In this case, we're going to use input. What we now have is a void setup that connects all of our pins, but eventually we'll have to delete the code that's inside of void loop because we don't want to just blink some LEDs. Instead, what we want to do is take a reading from that photoresistor. We actually have to create a new variable once again, and this variable is used to hold the value that the photoresistor is sending. What this means is photoresistor sets up the pin, but we need to use a new command that will take a reading from that pin. Let's go to our global variables and type int, an integer. Now let's call this a meaningful variable name. Why don't we call it photo reading? You can close with a semicolon as a line terminator because this doesn't need to contain anything just yet. What this means is that the variable has been declared, the program knows that it exists, but we will fill that or write to that variable with data that comes from the photoresistor. Data is just a fancy word in this case for determining how bright a room is by a number range. To do this, we will use the photo reading variable, and we will just simply declare it inside of void loop. At this point, we're going to assign it to a command with an assignment operator of the equal sign to check on a pin what is happening. Use the command analog read and pass it the parameter for the pin you want analog read to check. Close bracket and semicolon and your command is correct. You could also use a 0 in this case, but because we are writing with scalability and efficiency in mind, we want to declare our pins once so that we can use them multiple times just by the variable name. And this means that we only have to change our code in one place when the global variable is declared, in case we need to change our electrical wiring to a different pin. So what is happening here is that the declaration of a variable stores a command that is repeating. So the command checks the pin and it updates what is being saved in photo reading actively every time void loop repeats, which means the number that is in photo reading will always be changing. At this point, we're going to write an if statement, and we'll start with just writing the statement itself. We'll start with if indicating if and a bracket, and this will take parameters and create a comparison to a variable that we've declared and a fixed number. But hold on a second, we don't even know what numbers are being passed to photo reading. We need to use something special about the Arduino IDE called the serial monitor. What this is it's a serial connection from the computer or the IDE to the microcontroller itself. And what it can do is it can tell you things about what's happening on the board that you can't usually access just by looking at it. We're going to have to initialize a serial connection in our void setup. Let's call serial and add a period. Then type begin with the lowercase, watching your capitalization on serial, and pass it the baud rate. This is the speed at which it's going to be sampling from the microcontroller. And that is 9,600. We can now use, inside of the void loop function, a new command called serial.print and pass it some parameters. The parameters we'll pass inside of the brackets will be the reading we want to get from photo reading, the variable that's reading our photoresistor pin. Type serial with a capital S for serial.println and press bracket. Now you'll pass it the parameter you want to check, photo reading, and close bracket and end with a line terminator, the semicolon. Now when you press start simulation, the circuit will be on, the simulator time will be incrementing, but we need to access the serial monitor. If we zoom out a bit and you look at the bottom right-hand side of your IDE, underneath your text editor, it says serial monitor. Click on the serial monitor text to open it, and now select your sensor. If you slide the sliding scale from dark to bright, you'll see that the numbers increase. We plan on using the sensor data to make decisions in our void loop. We're going to compare the data in an if statement, but we need to know what the min and max values are. Let's create a comment by doing 2 forward slashes. This will change the color of the text and allow us to just write notes to ourselves. So we can see here that the 6 value is the min value that the sensor outputs. But what we want to know is the max value. What's great about this serial monitor is that it tracks all of the data, and we can actually scroll up to find the maximum value. In this case, this max value is 679. So we have the information that we need to know the minimum and the maximum working values that we can use, but we want to create interactivity not only when it is 100% bright or 100% dark, but in between these two values. Let's start by typing the if keyword and passing it a bracket. This will indicate there are parameters within these brackets. We'll pass it the photo reading variable, and we're going to use comparison operators. Of the comparison operators that are available, there are 4 comparison operators you can use. That is the less than symbol, the less than or equal to symbol, the greater than symbol, and finally the greater than or equal to symbol. What we could do at this point is use the value that is in the middle of this range, and that would be around 300 and so. We'll say 354 in this case, and close bracket. And now we'll use the curly brackets to indicate everything inside of this bracket, the curly bracket, will be run inside the if statement. Notice that there are 2, and now we'll start writing inside of the if statement. This is just like how you'll write inside of the void loop and inside of the if statement. They're like Russian dolls nested one inside of the other. So when this if statement becomes true, when the photo reading value that's stored in photo reading is in fact less than 354, and every number underneath 354, we can now set up the if statement to do something. And what we want to do is turn one LED on, so we'll use the digital write command. Let's pass the variable that we want to indicate the pin. In this case, we'll use the green LED, and we'll tell it to turn to a digital write of high, close bracket, semicolon for a line terminator. And now we're just going to simply write another if statement. Usually an if statement comes with an else condition, and this is a prime example of using an else condition. But what I want to show you is that you can use if statements to create these thresholds for decision making. They're basically logic gates, but you can create more than 2. You could create 4 in this case if you wanted to have 4 LEDs all controlled by the same sensor. Let's start by typing the if keyword using a bracket and passing it the same sensor, the photo reading. Now we're going to use a greater than comparison operator, and in this case we're going to set it to be a number higher than the first if statement that was set to be 354. We'll compare the second one to be 355. This way, both of these values will be considered, but they won't interfere with each other. Now we're going to digital write to the red LED a signal of high, and use the same syntax that you've used for the digital write command in earlier examples. But now we'll just run the simulation, and we'll have to notice something about the behavior of our program. Let's open the serial monitor and take a look at what our sensor is doing. So we can monitor the serial monitor from the sensor reading and check how the LEDs are interacting. Let's try to trip that threshold at 354. By dragging it up until it increments to 354, eventually that red light should turn on. But notice how both lights remain on and stay on when the conditions have changed. If we think about what we're asking the microcontroller to do, we're asking it to turn on the green LED when it is below a threshold, but then we never specify that the green LED should turn off at all. So in these if statements, there should also be a digital write that will turn the LEDs off so that it will work like a switch. Let's add digital write, and at this point, we'll call the red LED variable for that pin and pass it the parameters that it should have a low signal. Run the Start Simulation button and see if the behavior has been corrected. So when we increase the brightness in the room, or we increase the value that the sensor is reading, the red LED will turn off. But The green LED remains on and we're missing a command to instruct it to turn off in the second if statement. Please add the second digital write to turn the green LED pin to low. And now when you start your simulation and test, see what happens. And these two if statements are now working like a switch, complementary to each other, but they're including the fact that they'll have to instruct one LED to turn on while the other one should turn off. Depending on how bright it is in the room, it will either display a green LED or a red LED. Green LED for a dark room and a red LED for a very bright room. We've come to the end of the workshop today. We've covered how to create electrical circuits, how to program a microcontroller called an Arduino, and how to combine the two, the programming and the electronics side. If you'd like to learn more about the electronics side of this module in tinkercad, feel free to watch further videos as made by the Maker Studio. Take care and have a great day. See ya!